All right, common ion effect. Common ion effect is an example of Le Chatelier's principle, right, where we stress a system and the system responds to try to alleviate that stress. So the way this works, in the presence of its conjugate base, a weak acid's ionization is suppressed. So put a bunch of conjugate base in there, it shifts the equilibrium back towards the reactants. In the presence of its conjugate acid, the ionization of a weak base is suppressed. So again, put a bunch of conjugate acid in there, the product, and shift the equilibrium over towards the reactants. So we're considering a 1 molar acetic acid solution, right? It's a weak acid, so it only, low ionization. So I've got a 1 molar concentration. I'll lose X amount of acetic acid and make X amount of H plus ion and X amount of acetate. When I plug it into the equilibrium expression and solve for X, I get the H plus concentration, take the negative log and get the pH. All right, so 1 molar acetic acid by itself has a pH of 2.37. The idea is, in the presence of its conjugate acid, I am going to raise the pH. I'm going to get less H plus going into the water. I'm going to suppress the ionization of that weak acid. All right, so put a bunch of acetate in there, sodium acetate, into an acetic acid solution. You're going to raise the pH, lower the H plus concentration by shifting the equilibrium back towards the weak acid. So let's see what it looks like mathematically, right? So if you have a 1 molar acetic acid and 1 molar sodium acetate solution, you've already got a whole bunch of acetate in the solution. That's going to drive the equilibrium back towards the reactants and lower the H plus concentration. So I can ignore the change in the acetate concentration. The amount of X you're adding is negligible, and I can ignore the ionization, the initial concentration of the weak acid is changing. So X is equal to Ka, right? That's the H plus concentration. So now all of a sudden the pH has gone up, right? So where it was 2 point something without the conjugate base being in there, now with a bunch of conjugate base in there, the pH went up because you suppressed how much this weak acid ionized. All right, the Henderson-Hasselbalch equation is a very easy way to plug in when I have a common ion situation to solve for the pH. So, I don't know, it's easy to use a Ka too. You can do it either way, right? So we just did it this way a second ago, right? Solve for the Ka, right? You're not changing the conjugate base concentration very much. You're not changing the acid very much, so it's easy to solve for, right? The H plus concentration was equal to the Ka. But I could use this equation, right? So the Ka is equal to the concentration of the products over reactants raised to the stoichiometric coefficients, multiplying the H plus concentration by the ratio of the conjugate base to the weak acid is the same thing as products over reactants mathematically. If I take the log of both sides, I end up with this expression, right? The log of Ka is equal to the log of H plus the log of the ratio of the conjugate base to the weak acid. If I subtract the log of H plus from both sides and subtract the log of Ka from both sides, I rearrange it this way. The negative log of the H plus concentration is equal to the pH, and the negative log of the Ka is equal to the pKa. So this is the Henderson-Hasselbalch equation. So what it does is, if you know what the initial concentration of the weak acid is and how much of the conjugate base you have in the solution, you can just plug into this and solve for the pH directly if you know what the Ka is. And you know what? This is useful. It's a useful equation, so we're gonna be using it a lot or enough in this next topic. So for example, what is the pH of a solution where you've got 0.3 molar formic acid and 0.52 molar potassium formate? So it's easy. Just take these concentrations, right? The concentration of the weak acid, the concentration of its conjugate base, plug into the Hasselbalch expression, right? The ratio of the C base or the conjugate base to the weak acid, right? take the log of that ratio, plug in the Ka value and take the negative log and get the pKa, and that gives you the pH, right? The negative log of the H plus concentration is equal to the pKa plus the log of the ratio.